Model deployment is the process of making a trained deep learning model usable in a real-world or production setting. It means placing the model on a server or cloud platform so that it can be accessed by end users or integrated into other applications. The deployment process usually includes several key steps. Preparing the model for production. This involves converting the trained model into a deployable format, like a TensorFlow saved model or a serialized Python file. Setting up the deployment environment. This step creates the infrastructure, such as servers, virtual machines, containers, or serverless platforms, to host the model. Connecting the model with applications. APIs or other interfaces are created so that users or software systems can send data to the model and receive predictions in return. Import CV2. This line imports OpenCV, a library used for image and video processing. CV2 allows you to read, write, display, and manipulate images, for example, resizing, filtering, detecting edges. Import matplotlib.pyplot. Imports the pyplot module from matplotlib, a plotting library, typically used to display images, imshao, or create charts, graphs, like line plots and histograms. Note, this is usually imported as import matplotlib.pyplot as plt, so you can use plt.imshow, plt.plot, etc. Loads the TensorFlow library, used for machine learning and deep learning. TensorFlow helps you build, train, and deploy AI models. This line imports submodules from Keras, which is built into TensorFlow. Datasets, used to load pre-built datasets like MNIST, CIFAR-10, etc. Layers, contains various building blocks of neural networks, such as dense, conv2D, max pooling 2D. Models, used to create and manage entire models like sequential or model. This line loads the CIFAR-10 dataset, which is a standard image classification dataset included in TensorFlow Keras. Let's break it down. Datasets.cifar10.load data. Loads the CIFAR-10 dataset. CIFAR-10 contains 60,000 color images, 32 x 32 pixels. These are labeled into 10 classes, like airplane, cat, ship, etc. The dataset is split into 50,000 training images and 10,000 test validation images. Matplotlib.pyplot figure, fig size, 10, 10, creates a new figure, canvas, where subplots, images, will be drawn. Fig size, 10, 10, sets the overall figure size to 10 inches by 10 inches, which is large enough to fit 25 small images in a 5x5 grid. Matplotlib, pyplot, subplot 5,5 I plus 1, adds a subplot to the figure. Subplot 5, 5, I plus 1 creates a 5x5 grid of images. I plus 1 tells it the current position in that grid. Subplot positions start from 1, not 0. Matplotlib.pyplot.xticks removes the x-axis tick marks from the subplot to make the image cleaner. Matplotlib.pyplot.yticks removes the y-axis tick marks for the same reason. Matplotlib.pyplot.grid false turns off the grid lines inside the subplot. Matplotlib pyplot.imshow training docs images displays the IETH image from the training set inside the subplot. Matplotlib pyplot ylabel class names training labels adds a label class name below each image. Training labels, which fetches the label number, like 3, and class names, converts it to text, like cat. Matplotlib.pyplot show displays the entire figure with all 25 images arranged in a grid. This image is the visual output of the Python code you write, which plots 25 sample images from the CIFAR-10 training dataset using Matplotlib. What you are seeing is a 5x5 grid, 5 rows by 5 columns, displaying 25 images from the CIFAR-10 dataset. Each image has a label, class name, displayed below it. For example, frog, truck, horse. These labels come from the class names list. airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. This script builds a convolutional neural network, CNN, using TensorFlow's Keras API with a sequential model. It starts by adding a 2D convolutional layer with 32 filters of size 3 by 3 and RealU activation, designed to process RGB images of size 32 by 32 pixels. To reduce spatial dimensions and computational costs, a 2 by 2 max pooling layer is added. This pattern is repeated with additional convolutional layers of 64 filters each, separated by max pooling layers. After feature extraction, the model flattens the multidimensional feature maps into a one-dimensional vector, which is then passed through a dense layer of 64 neurons with RealU activation for further processing. Finally, the output layer has 10 neurons, corresponding to the 10 CIFAR-10 classes. The model.summary function displays a structural summary of all the layers. This is the model summary output of a CNN created using Keras sequential API. It lists all the layers in the network, along with their output shapes and the number of trainable parameters. The model starts with a conv2d layer that applies 32 filters to a 32 by 32 by 3 input image, resulting in an output shape of 30, 30, 32 with 896 trainable parameters. This is followed by a max pooling 2D layer that reduces the spatial dimensions by half to 15, 15, 32 without adding any parameters. Another convolutional layer with 64 filters reduces the size to 13, 13, 64 and introduces 18,496 parameters, followed by another pooling layer that further down samples the image to 6, 6, 64. The third convolutional layer outputs 4, 4, 64 and adds 36,128 more parameters. Then, a flattened layer converts the 3D tensor into a 1D vector of size 1024. This flattened data is passed to a dense layer with 64 neurons and 65,600 parameters. Finally, the output layer, dense, has 10 neurons, one for each CIFAR-10 class, with 650 parameters. The total number of trainable parameters in the model is 122,570, and all layers contribute to learning as there are no non-trainable parameters. This summary gives a clear overview of the model's architecture and computational complexity. This code trains a convolutional neural network, CNN, on the CIFAR-10 dataset. First, the model is compiled using the Adam optimizer, a popular algorithm that adjusts learning rates automatically to speed up convergence. The loss function used is sparse categorical cross-entropy, which is suitable for multi-class classification problems where labels are provided as integers. The argument from logits true is included because the model outputs raw scores, logits, not probabilities. The metric being tracked during training is accuracy, which tells us how often the model correctly predicts the class. Next, the model is trained using the fit function for 10 epochs. This means the model goes through the entire training dataset 10 times. During training, both the training accuracy and loss, as well as the validation accuracy and loss, are printed at the end of each epoch. For instance, in epoch 1, the model starts with a training accuracy of about 30.6%, improving to over 63.3% by epoch 4, with corresponding decreases in training and validation loss. This shows the model is learning to generalize better over time. The history object stores all the training data, loss, accuracy, etc., for later visualization or evaluation. This code is used to visualize and evaluate the model's training and validation accuracy over epochs. First, a figure of size 5 by 5 inches is created using matplotlib. The training accuracy, history, accuracy, and validation accuracy, history, val accuracy, are plotted against epochs. The x-axis is labeled epoch, and the y-axis is labeled accuracy. The y-axis is limited to values between 0.5 and 0.75 to focus on the performance range where accuracy improves. A legend is placed in the lower right corner to differentiate the training and validation curves. After the accuracy graph is plotted, the model is evaluated on the validation set using Model Evaluate, which returns the final loss and accuracy values after training. The parameter, verbose, ver2, is used to display the progress clearly. Finally, matplotlib.pyplot show is called to display the plot. This script helps to visually inspect how well the model learned over time and how it performs on unseen validation data. This graph visualizes the training accuracy and validation accuracy of a convolutional neural network, CNN, over 10 epochs. The blue line represents how well the model performs on the training data, while the orange line shows its performance on unseen validation data. Both lines begin at around 50% accuracy and steadily improve over the first few epochs. By the end of training, the training accuracy reaches approximately 76%, whereas the validation accuracy plateaus around 68%. From the graph, we can observe that the model initially learns well, with both training and validation accuracy increasing together. However, after Epoch 5, the gap between the two lines starts to widen. Training accuracy continues to increase, but validation accuracy fluctuates. This behavior may indicate overfitting, where the model performs better on training data than on validation data. The final model evaluation shows an overall validation accuracy of 66.5% and a loss of 1.0532, which are reasonable results for a basic CNN trained on the CIFAR-10 dataset. This visualization helps diagnose model performance and guides decisions on whether further tuning, data augmentation, or regularization is needed to improve generalization. This code demonstrates how to save a trained deep learning model, save an image from the dataset, and then reload that image using OpenCV. The first line saves the trained model in HDF5 format, H5, to a specific folder on the user's desktop. This format stores both the model's structure and weights, making it reusable without retraining. A warning appears indicating that the HDF5 method is used, which is acceptable for most use cases. Next, the script saves a single training image to the same folder using CV2 mWrite. Specifically, it saves the third image in the dataset, training images data, as a BMP file named sample.bmp. The true output confirms that the image was saved successfully. Finally, the code loads the saved image back into the program using cv2.imread, storing it in a variable called cve.image. This image can now be used for tasks like model prediction or display. These steps are essential for deploying machine learning models, where saving models and sample data is required for testing, inference, or demonstration purposes. This complete project demonstrates the full workflow of creating, training, evaluating, and deploying a convolutional neural network, CNN, using the CIFAR-10 dataset. It starts by importing key libraries, loading image data, and building a model with convolutional and pooling layers that learn to recognize features in images. The model is then trained and evaluated, with training and validation accuracy visualized to track performance over time. After training, the model is saved in .h5 format for reuse, and a sample image is saved and reloaded using OpenCV, simulating a real-world testing or deployment scenario. This end-to-end process equips learners with the skills to build and deploy their own image classification models using Python, TensorFlow, and OpenCV. Thank you for watching. If you found this tutorial helpful, don't forget to like, subscribe, and share it with your fellow learners. Keep exploring, keep coding, and stay curious. See you in the next lesson.